Page 5 of linear modeling. To investigate whether speed cameras have an impact on road safety, data was collected from several cities. The number of speed cameras in operation was recorded for each city, as well as the number of accidents over a 7-year period. So they have all this data for us. First thing they ask us for is to calculate the R value. We are not going to do this manually. We are going to do it using the calculator like we learned last time. Remember that first thing you're going to do is you're going to make sure that stat diagnostics is on by clicking on mode, and then you go down to here where it says stat diagnostic and make sure it's on. If it's not on, put the cursor on to on and click enter. Okay, then you're going to put your data into stat edit. So you go to stat edit. If there's already data there, you're going to clear it out by putting the cursor on top of L1 and L2 and pressing clear, not delete. Then you're going to put all the X data here and all the Y data here. I'm going to type that in offline. I'll be back in a second. Okay, we have checked whether stat diagnostic is on. We have typed our X data into L1 and our Y data into L2. Next step is to go to stat calc linreg in order to find our R value. L1 and L2 should be an X list and Y list respectively. Frequency list should always be blank. Calculate. And the R value is negative. Make sure you see this negative here. Sometimes people get confused because the equal sign is right next to the negative. The negative sign is very small. 0.878. So negative 0.878 is our R value. Describe the relationship between the number of speed cameras and the number of car accidents. Notice they're saying, describe the relationship between the X values and the Y values. All you need to do is interpret the R value of negative 0.878. Since it's negative, we say it's negative. And since it's 0.878, which is between 0.87 and 0.95, we know it is strong, right? Between 0.5 and 0.87, it's moderate. Between 0.95 and 1, it is very strong. And between 0.87 and 0.95, it is I think the only challenging thing about Part C is the fact that it doesn't directly ask you for negative and strong, so you have to figure out that when they say to describe the relationship or comment on R or whatever, they're asking you to say two things, positive or negative, and the strength. And of course, you need to memorize those values, but of course, on the final exam, you're going to write it down on your notes sheet. Plot the mean point, X bar, Y bar, on the scatter diagram and draw a line of best fit through the mean point. Okay, so in this case, we are going to do similar to the investigation, I took the pain out of it by I already graphed the points for you, all right? And so all you need to do is complete this graph. First step is you are going to label the axes. So number of speed cameras X, number of car accidents Y. So on the X-axis, we're going to write number of speed cameras. And then on the Y-axis, we're going to write number of car accidents. Okay, make sure you label the axes because that probably is worth a point on the IB exam and on any exam I give you. So the next thing we're going to do is we are going to plot the mean point on our graph. And the mean point we are, of course, are going to find using stat calc 1-bar stats. We already have L1 and L2 in stat edit, so all we need to do is just run stat calc 1-bar stats. Of course, I'm sorry, not 1-bar stats, it's 2-bar stats, sorry. And I was reminded of the fact that it was 2-bar stats because when I went into 1-bar stats, there was no place to put Y, right? Okay, so in 2-bar stats, you can put X list and Y list. I put L1 and L2 because that's what we used. And then I press, frequency list, of course, is blank. Calculate. X bar is 17, so I'm going to write down X bar is 17, and Y bar is 34. Okay, so that is my mean point. I'm going to graph my mean point on my axes here. 17 is here, and 34 is about there, slightly below 35, right? So it's about there. I'm going to graph the mean point as m. That's usually what they ask you to graph it as on the IB exam. And finally, it says to draw a line of best fit through the mean point. Of course, when we draw a line of best fit through the mean point, what we want is a line that basically goes through the cloud of points. Make sure you don't connect the dots. This is not preschool. This is IB, right? So I'm going to draw a blue line through the M point and going in the general direction of these points. Straight line with a ruler. There we go. Pretty good. Count the number of points above, count the number of points below. It should be approximately the same. But again, you're eyeballing this, so it's not going to be perfect, okay? But do the best you can. And you have to use a ruler. Where does your line cut the y-axis? So according to my graph here, it cuts it at 53 about. Okay, so I'm going to say it's 53. Interpret what this answer means. So this is super important. Like on the IA, it's like basic interpretation to interpret y intercept and slope and that kind of thing. In this case, the y-intercept is the number of car accidents when the number of speed cameras is 0. So when you don't have speed cameras, we would expect to have 53 car accidents. That is our interpretation. 53 car accidents when 0 cameras. Okay? All right. Let's talk about the least squares regression line. We already know how to do it because it's the same procedure as finding R, stat, calcul, and reg. We just haven't been looking at the output. So this procedure here is exactly what you've done before, okay? Write the expression which is minimized when finding the least squares regression line. Okay, so this is a very interesting calculus and algebra related procedure. If you are interested, you can take a look at videos online. It is an interesting procedure because you can understand every single step, and it's like it comes out very neat and nice. But you're not responsible for knowing it, so I'm not going to show it to you. But just to tell you how we got those really complicated looking procedures for slope, y-intercept, and R. We got those by trying to minimize the distance between the best fit line and each data point. So the vertical distances here are called D1, D2, D3, D4, etc. Right? We're trying to minimize the distances simultaneously between the best fit line and every single point. And then by doing that, we can actually find a single best optimal solution of a line instead of just eyeballing it and drawing it the way we've been doing up here. We are going to have an actual math solution. How do we do that? We're going to minimize these distances. How do you simultaneously minimize all these distances? Well, first of all, you need to be careful because like some of these distances are above the line and some of them are below the line. If we use a strict distance formula, we're going to find out that the distances above the line are going to be positive numbers. The distances below the line are going to be negative numbers. And if we add up all those distances, it's just going to be 0, right? So what you want to do is you want to define the distances as something that is always positive. And in math, the way we make things always positive is not to take the absolute value. We square it, okay? So we square. And the reason why that we square instead of taking the absolute value, if you're interested, is probably because squaring is a process which makes negative numbers positive, but it does it in a very nice curvy way, and then we can still use calculus. Absolute value, if you remember the function, it looks like a V. It's got this very sharp corner in the bottom. When you have very sharp corners like that, you cannot use calculus. So that is why squared is the preferred method, okay, of making negative numbers positive. So what we're going to do is we're going to take each one of these distances and we are going to add them together like we originally said, but instead we're going to square the distances before we add them together so that the negative distances become positive, and then we're actually have a quantity which is not going to end up being 0. It's going to be some finite number, and the better we optimize the line, the smaller this sum is going to be. So basically we're trying to optimize this, okay? And if you didn't understand that, don't worry about it. It's just for people who are curious and who want to start on the road to actually understanding where the formulas come from for doing linear regression. All right, let's do number 3. Now that we know that there's additional information in LinReg, maybe we can find out more information that comes out of it. Okay, so Steve wanted to see whether there was any relationship between temperature when he leaves for work in the morning and the time it takes to get to work. He collected data over a 14-day period. Okay, oh, by the way, we already have the data for the last problem in here. We already have StatCalc LinReg 1. Well, I didn't save the output, but let's do StatCalc LinReg again just to see what the output looks like for the last problem we did. Notice that it gives us an a value and a b value, and it gives us a template of y equals ax plus b. So you can see that actually a is the slope and b is the y-intercept, right? So actually the line which we estimated here by doing a best fit line by I, we could actually write an equation for a theoretical line which optimizes this by saying y equals negative 1.06, which is the a value, times x, plus 52.0, which is the y-intercept value, which is b, right? So you can see that like the actual math optimized formula is slightly different than what we found by graphing, because we found 53 instead of 52, right? So the best fit by I is not going to end up being the linear regression line. In your IAs, you're going to be doing actual linear regression lines because the mathematical solution is like a superior one. Okay, so that's how you get the equation of the line from the output. We just saw a case in here where the R value is strong, so we would definitely want to find the linear regression line for this case, because we know there is correlation. The R value is strong. Okay, so here we're going to do this for another set of data. We're going to have all this data input into L1 and L2, and we're going to rerun StatCalc LinReg, and we're going to see if we want to find the linear regression line in this case. So hold on, I'm going to pause the video and I'm going to type everything in to stat edit, and then we'll be back in a second. You do the same. Okay, I typed in my data. Now we're going to do StatCalc LinReg. Find our R value, which is what they asked us to find. Ooh, R value, negative 0.219. Is that good or bad? If you remember, it's pretty bad. Between 0.1 and 0.5, it's weak. So this is negative weak. When they ask us for the relationship between the variables, we put negative weak. When you have weak correlation, you do not try to find the line of best fit. You do not find the linear regression, because basically what you're saying is there is no correlation. So if there's no correlation, why are you going to find the linear regression line? Why are you going to find the line of best fit? You don't. You just stop and say there's no correlation. That's it. All right. Now, we started our first problem after we learned how to find LinReg, the linear regression line, by finding out when we're not supposed to find the linear regression line. Okay, so remember, if you have an R value that is as bad as this, you know, below 0.5, like on your IA or on the exam, you're not going to do this. Of course, on the exam, they're never going to have a linear, an R value that is below 0.5, because that would you would lose the opportunity to find the linear regression line, and you know they're not going to waste a linear regression problem by giving you a bunch of data that it doesn't have correlation, because then they're losing the opportunity to test you on whether you know how to get the A and the B value. So the A and the B value that appear here, you would never use this because the R value is too low. You would just not write it down. Remember that for your IA. Okay, 21E, interpolation and extrapolation. We talked about this in the investigation. We talked about trying to use your linear regression line, your best fit line, to make predictions between X and Y values that are outside of your sample cluster, okay? So when you are working inside the region where you have data points, you can be pretty confident that your linear regression line works pretty well to make predictions of relationship between X and Y. It's just that when you leave that relationship, when you go outside that region, then you shouldn't have confidence, okay? So that is the difference between interpolating and extrapolating. By the way, if you don't know what interpolating and extrapolating means trying to figure out these relationships between X and Y inside the region where you have data. That's interpolating. Interpolating, okay? Extrapolating is using this cluster to try to make predictions outside the cluster, okay? So extrapolating, like doing estimates outside data cluster, whereas interpolating is doing it inside data cluster. That's the difference, okay? All right. Mark the regions in the diagram at the right where you would perform extrapolating. Okay, let me erase all this. And let me just mark the parts that would be extrapolating. So extrapolating would be this region and this region. Okay, under what conditions is it valid to extrapolate? So you would be able to extrapolate if you know that the relationship for this whole region is linear, right? So if you know it's linear outside the cluster of data that you've taken, then okay, maybe you can do extrapolation then. But if you don't know it's linear, then you can't, okay? How would you know it's linear? Maybe the theory tells you it's linear, right? Maybe like you've done other experiments where you have found that outside this region it is also linear. Maybe you have read research that says it's linear. Okay, so that is when you would be able to make estimates using your linear regression line outside of this little domain here where you actually have data. Okay, that's it for page 5.